Good morning, everyone, and welcome to today's IAS lecture. And you can see that the topic is on the photocatalytic processes. And today is a very good day that we do not have photo that much. But we do research during rainy days. When the sunshine comes up, we have energy there. And revisit it because the process, the mechanism, many people talks about this, and even Professor Bahnemann himself, he started at very early career of his on this process of solar-related research from back to the PhD period of time. And then he worked briefly in Caltech, and then returned to Germany and works in the Institute of Solar Processes. And now he works as head for the Institute for the Technical Chemistry in the Leibniz University of Hanover. And if you have been working in this related area, especially for photocatalytic application in environmental field, and I think you must have read at least one of his review papers, which has been cited more than 10,000 times. And he revisited the mechanism of this process, and also he revisited our university. He had been here twice. And first time was nearly 20 years ago. And second time was about 10 years ago. So now he's here, as young as before. Let's welcome Professor Bahnemann.
Yes, thank you. Thank you so much, Professor Chen, and thank you for inviting me to come over here again. It's always a pleasure to meet you again. Meeting old friends is great, and it's a pleasure to be in Hong Kong again, for sure. I promise it's not my last visit. So, yes, I decided to talk about something where people think we know everything. We understand the mechanism. It has been in textbooks. Now there are quite a few textbooks on photocatalysis. Yet I have my doubts that we really understand the mechanism of this process. So I like to discuss some of our recent results where I feel it puts more question marks to the mechanism than we wish we would have. And but let me first introduce the people who did the work, because for sure I'm the one who travels, and somebody must do the work. And this work has been put together by Cecilia Mendive. She did her PhD with me and also worked as postdoc with me, and she's now a professor in Argentina. Dr. Hanan Mohamed, she also did her PhD with me. She's originally from Egypt, and now she has taken a professorship in Saudi Arabia. Dr. Jonathan Blow, he is German. He did his PhD with me, and after a postdoc period in Aberdeen, Scotland, he returned to Germany, and he is now working for the DECHEMA, which is a German institute doing research in chemistry funded by the German industry, and there he's building up a research group on photocatalytic research. Dr. Ahmed, she did her PhD with me, and she is now back as a lecturer working in Egypt. Dr. Montoya did part of his PhD work with me. He's from Spain, and he is now a research fellow back in Spain at the University of Madrid. Jenny Schneider is just about to finish her PhD with me. She is my top student right now, and she is the one with whom I can discuss all these things very well in my institute. Let me tell you a little bit about Hanover, because many of you probably have never been to Hanover. Hanover is in the northern part of Germany. You might have just seen Hanover on the news because very recently President Obama visited Germany, and he visited not Germany, he visited Hanover in Germany, and you might have seen these pictures also. This is a garden where Obama went also. It's a garden of the castle, which is very close to our university. This is not the castle, this is the main building of our university actually. And sometimes students and others, including professors, can enjoy beer gardens. Our university was founded as a higher trade school in 1831 by this nice gentleman, Mr. Kamash, and it then became the Royal College of Technology. Then we were still royals in Germany until the beginning of the last century, as you know. And it moved to this building that I showed you in the previous transparency, the so-called Welfenschloss. In 1899, we became a real university because the Kaiser himself granted the right to confer doctorates. And I think this makes a real university if you can confer doctorates. And it was still very small, and it started getting much bigger in size after World War I, when soldiers returning from the World War started to study various subjects in this university. This is how this Welfenschloss looked like before, a little nicer than in the picture. Some of these things were lost during all these war fightings. In 1968, the university turned into a technical university because we have all engineering subjects, and many people still call it technical university, even though this name only survived 10 years, because after 10 years, since we got the faculty of law and business and economics, it became University of Hanover. And reorganization always takes place. We have now 9 faculties in our university, and we celebrated 10 years ago our 175th birthday, and then the university was renamed again, and now the name is Gottfried Wilhelm Leibniz University, or just short Leibniz University Hanover. Leibniz, a scientist, not chemist, not a physicist, not a mathematician, everything. He was a real scientist, living part of his life, quite a big part of his life in Hanover, and that's why we took the name Leibniz. And you might have wondered what this is up here. This is the handwriting of Leibniz, and those of you who looked at this might see this is a binary code. Leibniz is the person who invented the binary code, and without him we wouldn't have any computers. So, and he did a lot of other things also, not only the binary code. Anyway, we now have about 25,000 students, and we are actually one of the largest, to say the truth, we are the second largest university in Lower Saxony, and you see the usual staff that is involved in this university, and this is one of our lecture halls here. This is my research group, and I'm very proud to present this to you because these are the people really doing the work. And you see, if you look at the faces, it's a very international group. I had, during the time I was working, people from really every continent of this earth. Right now I have nobody from Australia, but I had also people from Australia in between. And so this is really a very international group. And most of the co-authors are not on here. You see one co-author, this is Dr. Montoya, who is here. And in the middle you see my main co-author, Jenny Schneider, whom I rely on in my science very much. Who is Jenny? You are talking about some review papers. We have a recent review paper which just came out in 2014, a ChemRef paper which we entitled Understanding TiO2 Photocatalysis, Mechanisms and Materials. And I'm going to talk actually about this mechanism during my talk today. As you can see, it's quite a big review paper. And not only is it big, but it's also quite highly cited, even though it's only out since October 2014. It has already been cited 259 times, which makes it, interestingly, not only a highly cited paper, but even a hot paper in ChemRef, which I'm quite proud to say, and that's quite nice. And the main part of the work in this paper was really done by Jenny. Okay. Bringing you back to the chemistry, this is our chemistry building. You see it looks very old from the outside, and it is. But in the inside, we got brand new laboratories. It was renovated just a couple years ago, and so now it's nice, old outside, new inside. Before it was old outside and old inside, which was not so nice for the chemistry laboratories especially. Anyway, what am I going to talk about today? I like to draw your attention to the fact that besides the photolytic processes, there are a lot of thermal processes happening in photocatalysis. Actually, we use this all the time because usually quantum yields of processes are in the order of 10% at their best, which means 90% are other processes, and that must be thermal processes induced by light absorption. But normally you neglect this. You neglect the majority of the processes, which might not be too clever. Anyway, multi-electron transfer processes, I think this is extremely important because this is what we are always after. We want to reduce, for example, carbon dioxide into methane. That requires 8 electrons. Or we want to reduce protons or water into hydrogen. That requires at least 2 electrons. Oxidizing of water into molecular oxygen requires 4 electrons. So multi-electron transfer processes are important, and we found one way to visualize them, and that's what I want to talk about. Doping. Doping is something done a lot. You find a lot of papers talking about doping in photocatalysis, but what is the mechanism of doping, and how does doping of a photocatalytic process compare to doping of, let's say, a semiconductor for its use in photovoltaic cells? How do these compare? That is another topic I like to go into. Single crystals I find complicated, but I find very helpful, especially if we do photoelectrochemical studies on them. And then we also prepared our own label titanium dioxide and looked at its reactions. And what we did is we, instead of using oxygen 16, we prepared the material with oxygen 18 because we were interested to know where does the oxygen come from if you, for example, form carbon dioxide. And that's something that nobody knows, because it could be from the oxygen in the air, it could be from the oxygen in the water, but there's also a lot of oxygen in a material like titanium dioxide. So where does it come from? And do we actually know what is the oxidant in photocatalysis? This discussion has been going on forever, and I think we still are not really sure about the answer. Anyway, this is the simple picture of photocatalysis. This picture has been really around for 30-some years. What this shows is actually usually a nanoparticle. It might be quite a round particle, or it might be a little single crystal with dimensions of a few nanometers in diameter. And usually, and for titanium dioxide that is clearly the case, these are semiconductor particles. And the semiconductor, as you know, has a valence band and a conduction band. So here we are looking inside the particle and we see the band structure. So we see the energy inside the particle and we see how a photon comes here. And if the photon energy h nu exceeds the band gap energy Eg, then it's possible to promote an electron from the valence to the conduction band, like in photovoltaics. The same thing happens in photocatalysis. The only difference being that then the charges are not used to generate electricity, but the charges are used for chemical reactions. If you have an acceptor usually adsorbed on the surface of the nanoparticle, then this acceptor can accept an electron, becoming in the first step reduced to the respective radical anion, while a donor donates an electron and becomes oxidized to the radical cation. So one photon, if it's active, can generate one radical cation and one radical anion. That is a chemistry that is initiated by photocatalysis. However, already looking closely into a photocatalytic mixture, if you try to look at the nanoparticles, you use high-resolution electron microscopy. And if you look closely, and these were pictures done using a cryo system, which means you are deep freezing your system as quickly as possible with the aim to retain its geometry. And if you then look into the system, you see these nanoparticles and you see the atomic planes, and you see these are already little nanocrystals. These crystals, by the way, have never seen any temperature exceeding room temperature. So you can form single crystals at very, very low temperatures without any problem. But what you see also is that these particles tend to form aggregates. And these aggregates are not formed in a very arbitrary way, but they are formed in a very, very elegant way. These particles seem to see the atomic planes of the neighboring particle. And what you are forming here is one particle, second, third, fourth, and the atomic planes are parallel to one another. So what you're forming actually are little nanowires. But you are not forming this. The material forms it itself. The material just likes to be like that. That seems to be energetically the favored state. So the particles are formed, and at the same time you form these nanostructures, and wherever you look, you form them. So I think what we have to talk about is not individual particles, but we have to talk about self-assembled nanowires. Is it good or bad to have these nanowires? I think it might be good to have these nanowires because we have some indication that these nanowires can act as antenna systems. So you absorb your photon in one of these particles, then this energy as an exciton energy can move along this nanowire until it finally finds a particle where you do have the adsorbed electron acceptor and or electron donor, and then the reaction comes about here. So the place of light absorption and the place of reaction do not necessarily need to be on the same particle, but they can be remote from one another, and you should try and imagine this system not as two-dimensional. For sure it's three-dimensional, but this is hard to put on a transparency. But I'm sure this is a three-dimensional network of these nanoparticles that we have to deal with. So to talk about a single nanoparticle is an oversimplification for sure of the mechanism that is going on in this system. We have some proofs that not only energy is transferred, but also charges are transferred along these self-assembled nanowires. And the proof comes from some time-resolved experiments when we were looking at the formation of silver clusters on these nanoparticles. And the experiment was done in a way that we converted, so it's not a misprint here that I have 2 electrons, because you should remember it was an electron and a hole. What happened to the hole? The hole was, in this case, converted into a second electron by having an alcohol present. This alcohol, in this case, it was polyvinyl alcohol, which at the same time also acted as a stabilizer of the system. This alcohol is a very good electron donor. It donates an electron, fills up the hole, forms an alpha hydroxy alkyl radical in the first place, and this intermediate radical is now a very good reductant, even a better reductant than the electrons that you form initially, and injects a second electron, being itself converted to the aldehyde, injects a second electron into the material, so absorption of 1 photon effectively results in the formation of 2 electrons per particle. And what we have seen is the formation of these rather large, I'm talking about 20 to 30 silver atoms, rather large silver clusters within a few nanoseconds of the laser pulse. You already have these clusters. And this can only happen because each particle only absorbs about 1 photon in our experiments. So you only have 2 charges here. So you must envisage a migration now of charges along this 3-dimensional network, along these nanowires, and then you have a pool now of electrons that can be transferred all together to form these larger silver clusters in this system. And this seems to be a general mechanism of formation, because whenever we form as a photodeposition process these noble metal contacts, they are big. We don't form such a contact on each particle, but we form them on some particles exclusively, and the rest of the particles don't show these complexes. And actually, by the way, this electron transfer along these chains of nanoparticles is used, for example, in the dye-sensitized solar cells, also called Grätzel cells, where actually these charges are transported along titanium dioxide arrays. Now I'd like to talk about the results of an experiment which is actually only done as a blank experiment. But sometimes it's interesting, well, first of all, one should always do blank experiments, but sometimes it's interesting to try and understand what was the result of this blank experiment. And here we did the blank experiment when we investigated with infrared spectroscopy the surface, the interface between the TiO2 and the water layer. You do this in a setup where you use an ATR, which stands for attenuated total reflectance, infrared crystal, where the infrared light penetrates like this through the crystal. And if you look more closely, and this is now the layer of your TiO2 nanoparticles being in the order of a micrometer thick, and on top of that you have the aqueous solution, and actually it is this evanescent wave of your infrared probing light that penetrates through the TiO2 layer and through the water layer, and that can be utilized to probe what's going on at this interface water and TiO2. And we did this, and the blank experiment was just having nothing else in the system, no other molecules, nothing, just pure water. And what you can see is, yes, you can see the adsorption of water on the surface. You get certain bands here, and the interesting bands are around 1640 wave numbers. And if you look more closely, then you can see, oh, these are bands due to adsorbed water molecules, adsorbed hydroxyl. This is nothing new. This has been known in the literature for a long time, and we also see it. And now comes the blank experiment. without adding any molecule, and I showed you before, you need a molecule, an adsorbed molecule, to bring about a chemical reaction, because otherwise, if you have no molecule adsorbed, there will be no electron transfer happening. So now we did the illumination of just the TiO2 water interface, and we expected to see nothing, because it's a blank experiment. But we see something, and the something is pretty strong. We see with illumination time, it's UVA illumination around 360 nanometer light, which is absorbed by the TiO2, not by the water. So the water is not excited, the TiO2 is excited, and you see that these bands around 1600 and some wave numbers, they are increasing, and it looks quite interesting what we find here. So how can we explain what's happening? And one explanation takes into account this pre-existing network of nanoparticles. Now you excite the nanoparticles, you form your electron hole pairs, and they have nothing to react with. So what can they do? Just recombine. You get an electron hole recombination, but this will liberate a lot of energy. The band gap of TiO2 is 3.2 electron volts, so each recombination of an electron and hole will liberate 3.2 electron volts. And how is this liberated? There is hardly any luminescence, so it's not liberated as light. It's mainly transformed into thermal energy. 3.2 electron volts, if you do a little back on the envelope calculation, is plenty of energy to break bonds, like hydrogen bonds between the particles. If you break the bonds, you turn loose these agglomerates. If they turn loose, some might actually break completely apart. Here I just show you one particle breaking apart from these two nearest neighbors, and you have additional surface area available, and this additional surface area will be available for the adsorption of water on these molecules. So if this mechanism is true, this will explain why the infrared bands showing the adsorbed water molecules, why these rise in the system. But at the same time, if you intercalate more water into the system, you should get a little increase in the size of these systems. And we did some calculations, some theoretical calculations, how much increase in the height we would expect when we have more water in the system. If you have a higher layer of TiO2, this means that your probing evanescent wave would see more of the TiO2 and less of the water. With these calculations, and these are the results of the calculations here, this is illumination time, and this is the volume of water. So we are talking about microliters or 0.1 microliters, 0.15 microliters of water additionally intercalated in the system, which means your probed water layer goes down from initially 1.6 micrometers to about 1.4 micrometers, while the probed TiO2 layer with the water inside goes up from about 1.7 micrometers to about 1.9 micrometers. So this could explain what we see in this blank experiment. I'm sure there could be other explanations, but so far we didn't come about any other. And I have also not seen other people coming about trying to explain what we have been observing. Now let's switch gears and go to a photo process that is not only changing the system, but that is bringing about a chemical reaction. And we utilized some old material. When I was working at Caltech together with Michael Hoffman, we published a paper where we showed a very simple synthesis of titanium dioxide just using titanium tetrachloride as a precursor and water as the only reactant. I'm a physical chemist, and physical chemists don't know about very complicated synthesis, so I use this very simple synthesis here, titanium tetrachloride plus water, giving you TiO2 and HCl. Actually, the military uses this a lot. This is the smoke bomb used by the military a lot. That contains TiO2, which is not so harmful, and HCl, which is a little more harmful. Anyway, if you do this, you get nanoparticles which do not absorb any light in the visible and absorb only light below 400 nanometers. And if you look at their X-ray pattern, you see that they are already anatase nanoparticles. And now we did a very simple experiment. We took the system similar to the one I've showed you before. We just illuminated in an aqueous suspension containing methanol. And if you have methanol in the system, you have exactly the same reaction like I described with the polyvinyl alcohol. Methanol is a very good electron donor. When it gives away an electron to fill this hole, then at the same time you form this alpha hydroxymethyl radical. This is a very strong reductant with a 1 electron redox potential of about minus 1.4 electron volts. Very, very strong reductant indeed, because it wants to become formaldehyde. So it gives away another electron. So TiO2 gets a second electron. So overall you have a reaction where one photon generates 2 electrons in your TiO2 plus formaldehyde as the chemical product. And what you see is a blue coloration. This is something students in chemistry learn, I think, in their first or second year, that titanium, for the analysis of titanium, it's very nice to reduce titanium from 4+ state to 3+ state, because 3+ state shows a blue color. Nothing special about this. So this is the titanium 3+, the electron in the TiO2 being located at titanium sites. And if you do this continuously, this is illumination time versus the absorbance maximum is around, as you can see here, 600 nanometers. You can see that this absorbance goes up and up and up and follows very linearly. Here is the 0, 0 chart, so it's very linear, following Lambert-Beer's law, and you can determine an extinction coefficient. And it's very easy to remember. At 600 nanometers, the extinction coefficient is 600 reciprocal moles and reciprocal centimeters. If you have this, if you have these electrons in the TiO2, now you can play with them. And chemistry is playing, right? You go into the laboratory, shouldn't be called laboratory, should be called play yard, I think. It's, you go there to have fun. And having fun here means you can mix these electrons with all sorts of electron acceptors. And that's what we have done. An easy electron acceptor would be oxygen or hydrogen peroxide or. And now you can go on like this. And before starting with an easy electron acceptor, I take something where, which is a well-known electron acceptor and a well-known mediator for electrons. This is this molecule, mesoviologen. It's so well known that research has been starting with this molecule some 30, 40 years ago, because these positive charges, they like to accept electrons, and if they accept electrons, you get, before it's a dication, and once it accepts an electron, you get a radical cation formed, and this radical cation has a very strong color with a very high extinction coefficient of several 10,000. And so what you see is actually not that the blue color fades away, but you get additional blue color formation over time when you mix your electrons. In this case, we mixed 0.1 millimoles of electrons that we pre-illuminated in our TiO2 system with the viologen. This experiment is done in the dark with stop flow technique, and you can see how the signal of the radical cation goes up. This is for mesoviologen and this is for benzoviologen, and you see the reaction with benzoviologen is a little bit faster than the one with mesoviologen. You can also see bleaching of the blue color, if you, for example, take something like molecular oxygen in different concentrations, as you raise the concentration, you see the speed of the reaction goes up, and you see also that more and more of the electrons are consumed because you put more, and here about all electrons are consumed. And if you look more closely at the kinetics, you find a double exponential decay. The reaction apparently goes through two steps. If you look more carefully, you can find that the first step that you see is a reaction with molecular oxygen, going to the formation of hydrogen peroxide. Then you get a second step, which is the reaction of the hydrogen peroxide with the electron, and altogether you are utilizing 3 electrons to get from molecular oxygen to OH minus plus an OH radical, which then reacts further to do recombination to get more hydrogen peroxide, for example. You can also take hydrogen peroxide as a reactant, and then you can see its reaction going down. And again, you can stoichiometry follow this reaction by looking at how many electrons are there, and you can look at the kinetics of this reaction. So you can play around with these things. Take nitrate. Nitrate is interesting because nitrate has, again, a double exponential decay. First one using about 5 electrons, the second one about 3 electrons, altogether 8. And 8 electrons means it goes all the way to ammonia in this system. Or use copper 2 plus, uses 2 electrons going to copper 0. So that is what I mean. You can play with these systems and you know how many electrons are transferred and how fast this transfer goes. Let's look at a system that I've shown you before, the system with silver cations. Now you mix these silver cations with your electrons on the TiO2, and you see quite a complicated system, but you are able to unravel the system. You first see a phase 1 where hardly anything is happening here, no absorption of, not much absorption of the silver clusters is seen, but the electrons are consumed, and this forms the initial silver, the initial reduced silver atoms or clusters in the system. Then you see quite an increase of the absorption, the so-called plasmonic absorption, which is here, plasmonic absorption of the silver clusters on the surface, and a little more decay here of the electron absorption. So this always follows this absorption, and this follows the short wavelength absorption of the silver clusters. And finally, the silver clusters are all nicely formed, but electrons are still used. And what is happening here is now you have a catalyst on the surface of the TiO2. This catalyst is needed for transfer of 2 electrons to protons to form hydrogen. So hydrogen is only formed, and we know this from other experiments, and the whole world knows it. You need a catalyst for the formation of hydrogen, and so you have preformed the catalyst. Once the catalyst is there, then you form hydrogen, and as a matter of fact, yes, we detected also molecular hydrogen in the system by gas chromatographic analysis. Now you can change from silver to gold, for example, or to platinum or whatsoever, and you see the same thing. First reduction of the gold, nucleation, growth of the gold clusters until they become catalysts, and once they are catalysts, then you see the formation of hydrogen. And the reason you see all this is that the number of electrons that you had in the system exceeded the number of gold cations in the system, so we had still electrons left over that could then be converted into hydrogen. So these electrons are in fact active. They can be used to form hydrogen, which is then a fuel in the system. Next topic, doping in photocatalysis. This was an experiment which my student then, Jonathan Blow, started, and he came to me and said, doping doesn't work for my system. because he had looked at a system where he wanted to dope zinc oxide with iron or titanium, and his results were failure, because what he had done is he had compared pure zinc oxide with zinc oxide containing 0.5 atom percent of either iron or titanium, and as you can see, the efficiency, this is here now the efficiency not for alcohol oxidation, but this is the efficiency for acid aldehyde oxidation to carbon dioxide. And what you can see is the efficiency didn't increase. Why would he choose 0.5 atom percent? Because everybody in the literature says the magic number, 0.5 atom percent, that's the amount you should put in as a dopant. Well, but he was in the beginning of his thesis and he said, no, I continue. And so he put smaller and smaller amounts of iron and of titanium in the system, and his work was merited by finding materials which now do not contain 0.5% but 0.005%, or even here 0.002% of titanium, and they showed significantly higher activity, 3 times higher activity as a pure zinc oxide. So doping is possible, but here at a much lower level. Well, when he looked at his zinc oxide particles he had prepared, this is 100 nanometers, are pretty big nanometer sized particles. The ones I showed you before with the TiO2 were in the range of 3 to 4 nanometers in diameter. Here we are talking about 50 to 100 nanometers in diameter. So diameter seems to have something to do with the amount of dopants needed. So we looked into this and we developed a simple MENS model. What is a simple MENS model for doping of nanoparticles? Well, first guess is if doping should have any effect, you should have at least one dopant atom per particle. I mean, if there is no dopant atom in a particle, then doping cannot have an effect to this particle. This is, I think everybody in this room will agree to this. So this is the first thing we put in this model. So nothing in there, no doping. And the second thing is we felt, well, maybe if you put too many doping ions in the particle, what they could do if you, for example, put, this is the zinc oxide structure, the Wurtzite structure of zinc oxide. These are the zinc cations, these are the oxygen anions. And let's assume you replace one zinc cation as a nearest neighbor here in this distance A to this zinc ion by a dopant. And let's assume this was too much. Now this dopant acts as a recombination center, recombining the electrons that are in here and the holes which are trapped in the oxygen, and this would act as a recombination center for electrons and holes. That was our second assumption, and doing this you can get pretty nicely a dependence of the activity versus the doping ratio. This is now, the activity is linear scale and this is logarithmic scale. And this was our prediction of this simple-minded model. And these are the data points shown in the last slide. So the simple-minded model works. Again, I'm not saying that is the only model that you can find. You can find much more complicated models, for sure. But already a very simple-minded model works. Just taking into account you only need one, and if you have one as a nearest neighbor, this acts as a recombination center. If you have such a model, you should look in the literature, because many people have worked with doped material. Not so many with doped zinc oxide, but a lot with doped TiO2. And so we looked in the literature. Unfortunately, a lot of the literature did not contain enough data that we needed, because we needed data such as particle size measurements and things like that. But we found quite a few papers, doping of different sized TiO2s with different cations from iron to chromium to manganese and so on. And we got all these data and our own zinc oxide data, and then we just now changed the plot a little bit by again plotting here the doping ratio on the x-axis, and on the y-axis now the particle diameter. And you see the optimal area according to our model would be the ones above the area of the empty particles, not doped, and above and below the area of the clusters where you have recombination centers. And these are now the data points from the literature, and they are all in this optimal area. These are actually our data points here from the zinc oxide. If you prefer other plots, you can plot, for example, the average number of doping atoms per particle as a number of the particle diameter. And if you start with very small particles in the area, this is 10 nanometers, this is 1 nanometer, so this would be 3 nanometers diameter. So you see you need about 2 doping atoms per particle to reach the optimal doping. As you increase the particle size, then you come here to about 100 doping atoms. Or you can say, let's look at the doping ratio in atom percent. The very small particles, you are at this doping ratio of 0.5 atom percent. And with the bigger particles reaching 50 to 100 nanometers, you are at this optimal doping ratio of about a ppm or a few ppm. So we are at very small doping ratios here. When doing this study, we also observed other things. So these are the results. Now, we also checked with the zinc oxide, not only titanium and iron, we checked copper and ruthenium and so on. We always compared it to the pure zinc oxide, and we noticed some interesting features when we worked with manganese. Manganese, once again, at very low atom percent, showed very high efficiency for UV photons. So just as titanium or iron, same thing. However, there is a second area at very high manganese modification ratio where we now find activity in the visible. And if we look at these, let's say, doped zinc oxides at high atom percent, you see they absorb also visible light. And this visible light effectively can bring about our reaction. Still, we are using the same test reaction, oxidation of acetaldehyde in the gas phase. What do we think is happening here? We think if we have a lot of manganese, it's not only incorporated in the in the zinc oxide, but it forms islands on the surface. And these islands probably contain manganese 3 or manganese 4. And these islands can be excited directly. An electron from the valence band can now be excited by visible light photons directly to these deposits on the surface. This is something found with TiO2 for so-called grafted TiO2. Hashimoto, for example, and his group has done a lot of work on this, and we find a similar effect here for manganese on zinc oxide, probably as a manganese oxide on the surface. And if the electron goes there, then the reduction reaction will occur here, while the oxidation reaction still is using the holes in the valence band to oxidize our organic compounds, our acetaldehyde, to carbon dioxide. With ruthenium as our dopant, we found another interesting thing, and this is that we now found once again a visible light activity at high modification ratios, doping ratios, but also the UV activity was not highest at very low doping ratios, but was highest at about 0.1 atom percent. And again, we find very strong coloration. Now the absorption maximum is already in the near infrared. What is happening here, this is our mechanism which we propose. We think that ruthenium is indeed incorporated, forming new mid-band gap states in the zinc oxide. And you also have ruthenium oxide, which is well-known catalyst on the surface of our zinc oxide. This catalyst will act as an electron transfer catalyst, will not be involved in the photo process, but the photo process can now be induced by really red light. 1.5 electron volts is sufficient because now you can excite electrons from the mid-band, these filled mid-band gap states, to the conduction band. So you have a process where the electron donor is oxidized by the oxidized mid-band gap states rather than by the valence band materials. That would be an interesting material indeed for visible light activity because you can utilize really red light here. A complicated issue is always when you want to understand what somebody in electrochemistry tells you. And luckily, there are good colleagues around, like Professor Laurie Peter, who has just retired, but who is still extremely active, probably at least as active as before. And Laurie Peter has done theoretical calculations to analyze data of electrochemical measurements in single crystal semiconductor electrodes. And the interesting thing, or one mechanism that he has looked into is the oxidation mechanism of water. If you think, how is water oxidized? When is the oxygen-oxygen bond formed? And you can envisage many mechanisms, but let's just look at two different mechanisms here. You can envisage first the oxidation of a surface hydroxyl group forming a surface hydroxyl radical, which is then further oxidized by a second hole, and then you get the generation of oxygen. Or you can say, no, that's not the mechanism. The mechanism involves this, but this twice. So you have two neighboring sites which are oxidized, and then these two neighboring oxidized react with each other. This is called case 2. And the interesting thing is, if you do your calculations and you look at the rate constant for electron recombination and for electron hole recombination and for the trapping of the holes, both of which you can get experimentally. The theoretical predictions are that in both cases, as you increase the voltage in the system, the recombination rate constant decreases. So this cannot be used to discriminate between these two cases. But the trapping rate constant increases here with increasing potential, and it decreases here or stays almost constant as a function of the potential. So we did some experiments like this, and what we found is this was done here now with this is the potential again here, and you see here the recombination rate constant decreases, yes, and this was done with rutile, and we also did it with anatase single crystals, and you see that the trapping rate constant is found to increase here. These are data from incident modulated photocurrent spectroscopy, so you are modulating your incident light, so you have a constant light which you then modulate, and these are the data you are getting. So we are pretty sure that, going back to the cases, that we are in case 2 in our system. Case 2 can have different ways of reacting. One way would be that you are oxidizing mainly the terminal hydroxyl groups, but we don't think this is happening. I tell you in a minute why. We think what is happening is that you have bond breaking in your TiO2. That the oxygen that we are talking about is not an oxygen from the water, but is an oxygen from the TiO2 matrix. So your case 2 means that you oxidize this bridging oxygen and probably this bridging oxygen, and then you get an oxygen-oxygen bond through the oxygens from the TiO2 matrix. Why do we think this is happening? We think this because we prepared our own TiO2. Our TiO2 containing not Ti16 but Ti18 in the matrix. We use the same synthesis that I showed you before, the synthesis where titanium tetrachloride reacts with water, but now it's not H2O16, but it's H2O18. So it's easy to synthesize, just costs a little more money. And then we looked at the reaction, at the oxidation of benzene to form carbon dioxide, and we checked with mass spectrometry the amount of carbon dioxide containing O16 and the amount of carbon dioxide containing also some O18, which can only come from the TiO2 in the system. And we did this with normal TiO2, with the usual TiO2 16 and with the O18 labeled TiO2. And the blue curve shows you the mixed oxides, the C O16, O18, and the black curve shows you the normal CO2 with O16s. And you see in both cases you get some CO2-18. This is what you expect. There is a natural amount of O18 in the water already. You always buy some O18. Not a lot, but you buy some, and you see here this scale is much smaller than the other scale. So in order to analyze the data, it's better to look at the ratio of the mixed carbon dioxide and the pure carbon dioxide. And if you do this, you find that indeed on the labeled TiO2, initially you form much more from the mixed carbon dioxide. Then they behave the same, but they should behave the same because we are only talking about the top level of our TiO2 where the bond breakage occurs, and then you get a repair. So the whole system should be regarded as a dynamic system. So you are breaking these bonds, yes, you are losing these oxygens, yes, but then they are replaced by all these oxygens from the water, and then you have a surface of this TiO2 particle containing now O16. The bulk still contains O18, but the bulk has nothing to do with the reaction. This is why we see this transient over the first, let's say, few minutes of the reaction. But we should forget this notion of a constant TiO2 surface. The surface is apparently dynamic. This is the mechanism in a more complicated way. And now let's come to the final point, final few minutes, talking about laser flash photolysis work. This is how I started. As a young postdoc, I started doing laser flash photolysis work on TiO2, paper published as early as 1984, so well over 30 years ago. We published this paper in my early postdoc studies before I even joined Caltech, and we saw the spectrum of the electrons. I've shown you this already, very stable in the absence of oxygen, and we also saw a spectrum of the holes at around 400 nanometers, and we looked at the reactions of these beasts. This is very old history, and this is my young colleague, Jenny, at work. And we know that the mechanism is at least as complicated as this, that the electrons and holes you form, they will go into traps, and these traps can act as recombination centers. They can also recombine with untrapped charges, and so on, and you can also have direct recombination. So this is a reaction you want to bring about, but all this is a very complex system. There have been nice review papers, for example, by Yoshihara and co-workers, showing that besides the trapped electron that we had discovered in 1984 and the trapped hole actually has a second band in the near infrared, and the bulk electron can also be observed in the infrared, so you can observe all these beasts. And what are these transients? Well, the trapped electron is, as I showed you before, is trapped on a titanium 4 site. The trapped hole is most likely trapped as a trapped bridging oxygen, and the trapped another trapped hole might be terminal oxygen here in the system. So we looked at powder samples in reflection mode. That's the first time that real commercial powders have been investigated. We find an interesting thing when we do this. We find the spectrum which resembles the whole spectrum, but we don't see any trapped electrons. There's nothing to react with, so where are the electrons? We don't see the electrons. We can look at the decay kinetics, different decay kinetics, bi-exponential fit seems to work, but nothing what we see from the electrons. No matter whether we have vacuum or atmosphere, we don't see electrons, we only see trapped holes. Yes, we see electrons, but only if we put a hole scavenger. Our old friend methanol now put as methanol vapor on top of our commercial TiO2 powder. Then we see the spectrum of the electrons and no more spectrum of the holes. But the holes, when we see the holes, we don't see electrons. We identified these transient as the trapped holes. The kinetics tell us there is more than one trapped state for the holes. So maybe you might also invoke something like an ozonide on the surface. And the decay process seems to be the first decay are the untrapped electrons with the trapped holes, and the slow process is then the recombination of the charge carriers. Electrons are not trapped in the absence of hole scavenger, something we still don't understand why. Then we've also looked at other phases except for anatase. What I showed you before was pure anatase. We looked at rutile and bruchite. And again, we did the studies. You see the maxima are shifted a little bit in bruchite and rutile as compared to anatase. The kinetics in bruchite are faster and rutile are slower. Anatase is sort of in the middle. These are our particles that we looked at. And the interesting thing is, if we compare the decay kinetics at different bruchite contents with the photonic efficiency, with the quantum yield of processes at these materials, you see that as the bruchite constant is increased, the decay kinetics are increased, and the efficiency is also increased. So faster decay kinetics means better efficiency. That is a little counterintuitive at the first stage, because you think the longer the charge carriers live, the higher their efficiency is. But no, if they live shorter times, then they're apparently much more active in the system. And this is the final summary. So the transient absorptions are shifted in the order bruchite, anatase, rutile. The rate constants depend on the crystal phase, and the decay rate increases with increasing bruchite content. A higher rate constant apparently means a higher reactivity of the trapped charge carriers, and this is shown by the higher photocatalytic activity that we found in the system. So this brings me to the end of my presentation. I carried you through some bits and pieces of the mechanism of photocatalysis. I think we should investigate much more thermal processes in photocatalysis, because we can learn a lot from these majority processes to what is happening with the minority processes, which are our chemical reactions. Multi-electron transfer processes, I think the system is quite neat that you can store a lot of electrons. You can store up to 100 electrons per nanoparticle, no problem. Doping, I think our mechanism is simple, but it seems to explain what's going on in doping in photocatalysis. combining the single crystal studies with the labeled titanium dioxide studies shows you something about the reactivity of the surface, and that the reactions are actually occurring in a fashion where the surface is degraded and rebuilt. So we should not think of a static surface in a photocatalytic system. And the oxidant, that seems to be really complicated, and the more reactive the oxidant is, the more active seems to be the photocatalyst, which I found quite interesting from these time-resolved studies. So if you want to read more on photocatalysis, why don't you look into these 2 volumes which have just appeared from the Royal Society of Chemistry, together with well-known colleagues like Dion Dionisio, Gianluca Lepuma, and Genoa Ye from United States, Britain, and Japan. We edited these 2 volumes, and that gives you 1,000 pages of to read on photocatalysis. And I'd like to thank you very much for your attention, and I hope I was able to show you some new features and some more things I still don't understand in photocatalysis. Thanks very much.
Yeah, very nice talk. Yeah, for the last topic you talk, so if you don't have a whole scavenger, you cannot see the trapped electrons. So
right.
Where are the electrons?
Yeah, the only thing we think is that the electrons are probably still somewhere in the conduction band, not trapped in the system. We have now we are now changing our system to be able to also look at these transient absorbance in the infrared, because I showed you these data taken from the literature where people say you can do spectroscopy of the non-trapped electrons in the infrared, and now we have a new detector which goes beyond 800 nanometers, so we should be able to try and look for the question, is it untrapped electrons? But why are they only trapped when the electrons are eaten up? I don't know. I find it very, very hard to understand.
Another question is for ruthenium, doped one, why UV is not actually active, right, for the activity, UV activity?
Yeah. I don't know.
Because usually UV activity is much higher.
It's much higher, yeah. But here it was. Yeah, this is also interesting, and the nice thing is that you see this really strong visible light activity if you use photons of 1.5 eV. I mean, clearly this is visible light, or I mean, this is red light, right? Where are we looking at now?
I would like to ask you 2 questions, and the first one is about the nanowires that are self-assembled.
Yeah.
So my question would be, are there any efforts to control the shape, the formation of these nanowires? Because I imagine that depending on the length, on the structure of these nanowires, it should affect it
should very much affect this, and no, so far I haven't come across anybody doing this, but this is, I would think, a very, very meaningful research topic that should be taken up, for sure.
And the other question would be, you already did the experiment with the labeled titanium dioxide, and you show effects of signal intensity, but you don't show any results on a mass spectroscopic analysis of the product, which should also be highly informative about the role of the oxygen from the titanium dioxide in the reaction.
The data I showed, that was the product. It was CO2. This is the these are the data from the mass spec. These are the mass spec signals from CO2 with O16 and CO2 with O16 and O18. So these are the final really the final products, because I mentioned it only briefly. What we looked at was really the oxidation of benzene in the system. So we started with quite a complex molecule, and then just this is really the final yield, and this is why it's not worthwhile to look for. You could have asked also the question, why don't you find any CO18 twice? We don't expect this because there are so many steps needed until you finally get to CO2 from benzene that I wouldn't expect to see two oxygens from the TiO2 incorporated.
Thank you, Professor. I want to ask one thing. In case of the doping process, what is the exactly mechanism, the new thing in your case, when silver doped with the titanium? The mechanism behind?
Silver with...
Silver or metal, I mean the doping process. What will happen, the conduction band and the vibration band, and is there any...
Okay. I personally will never talk about doping when I talk about silver, gold, or something like that, because this is a formation of nanoclusters on the surface. So what you are forming actually, and this is a very good question, because I didn't really talk about this, what you are forming is a noble metal nanocluster on the surface of your semiconductor. And then in the dark, this means you have an equilibrated energy level. So your redox potential will be controlled by the redox potential of the silver cluster, the gold cluster, and so on. And now, so this is the Fermi level. The Fermi level is dictated by this cluster you have there. So you will have different Fermi levels. I showed you that only a few TiO2 or zinc oxide particles have this direct contact. They have a different Fermi level in the dark than the rest. 90% still have Fermi level of the TiO2 and not controlled by the silver. Now you illuminate the system. And upon illumination, you form in all the particles your charge carriers. And it is because of these contacts with the metal that the electrons go the way they want. This directs the electrons in this ensemble to these positions. This is like an electric field. You have a built-in electric field in your system. I'm glad you asked this question because it is complicated, but this generates a built-in electric field that drives the electrons to these positions. That's why you have the electrons going there, and you need them to go there because there they react with, for example, protons forming hydrogen.
So how big is the metal size, cluster size?
A little smaller than our TiO2 size, so we're talking about 2, 3, 4 nanometers in diameter. So, but pretty big, imagining that you usually also only take something like less than an atom percent of your metal, which means really you cannot have a metal contact at each semiconductor particle because the amount of metal you put is very small. It would be a disaster if you would need a contact at each nanoparticle in the ensemble, because then you would need as many metal particles as TiO2 particles, and this costs you 100 times as much as the TiO2, right? Even if you take just silver, I mean, not talking about gold or platinum or something like that.
Hello, Professor. For the part of your work on the iron-doped titanium oxide, you got the titanium oxide chain, right? The iron-doped titanium oxide.
Yeah.
So what's the possible reason for the formation of the titanium oxide well? And what's the advantage of the nanowire compared with the isolated titanium oxide particles?
Well, I think the advantage is clear that you have the chance of charge transfer and also even energy transfer through these nanowires. The question, why does self-assembly occur, I have no ideas why these particles. According to my experience, I always say that these nanoparticles have a memory. They still know where they come from. Apparently, a TiO2 nanoparticle remembers I was at some stage a titanium tetrachloride or a titanium tetraisopropoxide or something like that, because they behave differently. But why they do this, I really have no answer to this. I would wish I had an answer to this. Why is self-assembly occurring? I don't know. Why this? I think I have an answer to the question, or I have an idea why the self-assembly is occurring in such a way that you really form single crystal nanowires. I think really this is an energetic process, and this is a minimum energy rather than having the single crystals oriented in different ways. I think this answers this question, but why they do it in the first place, why they don't stay separate, because, from electrostatic point of view, they should stay separated because we're talking about nanoparticles with a lot of positive charges on the surface. So kinetically, they don't like to get together because they have the positive charges on the surface, yet they do this for whatever reason. I would be happy to know this.
Thanks, Professor Bahnemann. Did I make the right pronunciation?
This was very close, very close.
Okay.
Bahnemann.
Bahnemann, okay. Excuse me for this. And
now you know why everybody calls me Detlef, because the Detlef is much easier, right?
Actually, I know I don't quite capture how do you monitor the trapping of the electrons and holes? You just monitor their color change, right?
Yes. This is lasers. This is laser spectroscopy. I can show you what we are doing. I went through this very quickly, or I didn't go through this at all. What you have is a normal spectrophotometer. You have a monochromator. You have your cell where your reaction is occurring, and you're analyzing light. So this is a normal spectrophotometer. And what you do is your lamp to excite this is now a laser. The laser is just sends out nanosecond long pulses. So you excite only for a maximum, let's say, of 5 nanoseconds, and then during this time you generate your charge carriers and you analyze afterwards the color change. And so it's a time-resolved spectrophotometer that we are looking at.
So generally, if your electron is not trapped by the titanium ions itself, you cannot observe it, right?
This depends, because this is what you find in the literature. This nice review of Yoshihara, he showed, or he took data of whatever group, showing that the bulk electron, the non-trapped electron, should lead to a transient absorption. This is normalized. You should not take it for granted that it's the same height. So it's pretty small, but they have seen transient absorption above, let's say, 1500 nanometers for the bulk electron. Don't ask me what transition this is for the bulk electron. I don't know. Is it a transition to a higher state? I have no idea why it should absorb light of, let's say, 2000 nanometers or something like that. That is much less than 1 electron volt, right? So what is the higher level? I don't know. And it's not really a spectrum. It just goes up, right? So it just shows you that there are higher energy levels that can be populated.
Okay. So in your case, it means that the electrons you do not observe is neither trapped in the titanium nor in the bulk electron reservoir, something like this. Mm-hmm. And so do you have the, like you previously showed that there's some deposits of the small nanoparticles on the surface of titanium oxide. Do you have this kind of thing in this system?
You mean in the system when we have okay. Yes, we also did these experiments when we had platinum or silver or something like that on the surface. And if we do this, then we see an increase of the signal of the trapped holes, and the electrons are then only trapped at these noble metal sites, and there they don't show any transient absorption. Yes, we have done this, and this increases the absorption of the trapped holes.
Do you mean if you put these guys in that, the absorption by these guys are very significant?
Yeah, right. Mm-hmm.
Okay. So because I recently read some paper that if we have at the nanoparticle, the electron-hole pair will recombine in an auger manner. So it will excite the electron to another place. So, and this process is very, very fast. I wonder whether this recombination really contribute to the separation or the missing of electrons.
I'm sure it will contribute. Yes, actually, we are quite sure that this Auger process occurs in this system, and especially under these high laser intensities. We should not neglect the Auger process, but even more, I've shown you that thermal processes should not be neglected, and we are pretty sure that also in these systems, these high laser intensities can induce thermal processes, and we have some indication, I didn't have enough time to go deeply into this, that you can even get a transformation due to this energy from anatase to rutile in this system. So we find, after just one or two laser pulses, we find now already some rutilized crystals. So this thermal energy is sufficient not only to bring about the Auger process, I totally agree with what you cited from the literature, but also bring about the transformation to the thermodynamically more stable form, which is the rutile form. And we have seen a similar thing also when we looked at hematite, at alpha iron oxide. Part of the hematite with the laser pulses was transferred into maghemite and magnetite. So thermal processes are really abundant in all this, so thanks for the question.
Okay, thank you very much.
Or just permanent change?
It looks like permanent change.
Good. Any other question? Well, if not, let's thank Professor Bahnemann again.
Thank you. Thank you very much.